Thank you for the introduction, and thanks to the organizer for this nice workshop and for the opportunity to be here. The theme of the workshop is Spinoptics. We don't have any spin, unfortunately, in this talk. I'm going to just talk about artificial atoms, which are two-level systems, so there's some resemblance. And unfortunately, there's no light as well. There's going to be microwave photons, which are photons if you believe it. So with this summary, I'm going to tell you more about ways of realizing directional light-matter interactions with superconducting qubits. A very brief summary about our group. We are a newish group at Caltech. Broadly defined, our work is on realizing photon interconnects for superconducting qubits. We realize microwave to optical transductions with the goal of up-converting quantum states from superconducting qubits to optical domain, and someday realizing long-distance interconnects. On the other hand, on the shorter distance, we use microwave photons, which are naturally emitted by superconducting qubits, and route them in waveguides for connecting qubits, which is going to be the topic of my talk today. These are my group members who contributed to everything that I'm going to talk about today. And with that, I have to tell you about the motivation for why we're doing this. A big part of the motivation is this idea of modular quantum computing. The idea is that with this progress in making more and more sophisticated quantum systems, at some point, especially with superconducting qubits, we have to move out of the chip. We run out of the number of the real estate on a chip, and we will be limited by the number of qubits we can fit on a chip, and we would have to link some sort of mid-sized quantum processor with communication links to make something larger. Of course, this is the more applied view on the things, but realizing complex non-local connectivity between qubits is inherently interesting and would be potentially useful for other types of problems in quantum networks and quantum simulation experiments, which is why we care about this topic. Now, to give you a very brief summary of how microwave interconnects look like for superconducting qubits, I've picked out these photos from previous work. As I said, superconducting qubits can emit and absorb microwave photons naturally. Microwave photons can be confined and routed at cold temperatures using some sort of cable or on-chip waveguide. Here you can see different experiments realizing connection between two qubits on the chip scale, on the meter scale between two separated chips, and on a much larger tens of meters size scale where you have multiple cryostands. So the main form of the experiment is something like this: qubits connected by a cable in between them. Now, depending on what experiment you look at, there are different regimes of parameters for communication between qubits. This most simple case of having qubits separated out by a segment of a cable can be understood as thinking about the cable as a multimode cavity. So this is actually just a cavity QED case. If you take care and set the frequency of these qubits to not collide with the discrete optical modes in the cable, you can actually realize photon-mediated interactions between the qubits, which can be used for state transfer. And I mean, of course, this is a multi-mode cavity QED picture, but the general scheme is very similar to what you do with a single cavity. This works really well. The issue is that if you go to larger distances, this cable becomes long. The free spectral range between the modes becomes really small, and at some point, this scheme becomes really, really slow. And there, you really want to think about other ways of doing this. Another approach is to use your qubits as emitters, have a quantum state prepared in a qubit, let this state radiate fully into a photonic wave packet. Here, you can think of mapping a stationary qubit to a traveling qubit, which is just the Fock basis of this traveling wave packet. And then on the receiver node, you can do the time reverse version of whatever you did on the sender and absorb the microwave photon. The nice thing about this scheme is that you have absorption and emission, and as far as you don't have loss in your cables, you can go to any distance and run this protocol, unlike the previous one. And the other additional benefit is that you can, in principle, think about running a long cable between many qubit nodes and then think about ways of realizing connectivity between each qubit pairs. However, to avoid back reflections in schemes like this, you need some sort of unidirectional photon propagation, which you can do using circulators. These are non-reciprocal components in the microwave domain. You can just buy them and attach your cables here, and they work fairly well, but they tend to be rather large and somewhat lossy, which is not really great. So, hence the motivation for making qubits with native directional coupling. So the idea is that if we can make these qubits with unidirectional emission, as I said, we can link them all with a single radiation channel and then, for example, pick the frequencies to realize two connection between each two. And as we will see, interestingly, in these cases, we will not be sensitive to any physical separation between any two qubit pairs. Now, there is going to be a range of more interesting things you can do with arrays of chiral or directional emitters. This has been studied relatively extensively in the theoretical domain. One interesting phenomenon is that this idea of cascaded quantum systems where you could have emission from one emitter being reabsorbed by another emission down the road, but the reverse cannot happen. So depending on how you write your master equation, you might get a Hamiltonian that looks non-Hermitian, which gives rise to interesting physics. On the other hand, you can study the propagation of light field in an optically dense system of these chiral emitters, which can realize non-classical states of photons, which might have some relevance for quantum metrology problems. I'll tell you more about what we can do with these types of systems later on in this talk. Now, one last piece of information on the introduction, and that is what we are doing here is by and large motivated by what has been done in the optical domain. These are some past results from Lodal group and Roshan-Boytel group, where unidirectional emission from quantum emitters has been realized in the optical domain. So here the idea is that if you have a strongly confined electromagnetic field in nanophotonics waveguides or nanofibers, you can get modes that propagate to the right and to the left. And locally, you can have these propagating electromagnetic modes to have orthogonal circular polarizations. So if you have an emitter that has a polarization-sensitive transition, you can use that to get one of the handednesses of the polarization propagate in one direction and the other one going the other way around. Unfortunately, for superconducting qubits, something like this is not easy to imagine. They are linear structures, and the electromagnetic field produced by them is transverse. So we don't have any interesting polarization-sensitive transitions. In order to engineer transitions, you can think about more complicated systems. For example, you can think about two qubits rather than one, which together can form directional response. This is some theoretical scheme proposed by Nakamura's group, where you take two superconducting qubits separated by a distance that happens to be lambda over 4, lambda being the wavelengths of radiation resonant with the qubits. And if you prepare these two qubits in an entangled state with this I factor in the state, you can get the system to radiate preferentially into one direction and not the other one. So this idea actually was recently demonstrated in an experiment by Will Oliver's group at MIT. Single photons are prepared in a superposition state of two qubits and launched in one direction or the other, and it works remarkably well. However, this is a rather complicated experiment. You need to have precise matching of parameters for two emitters and time domain control over the couplings. Besides, if you try to drive this system strongly, of course, the single photon response is fully directional, but there is a excited states of two qubits. You have seen the level structure of two emitters many times today. I'm not going to show it again. But this excited state is actually non-directional in this case. So the chiral emission is only valid for weak drives, which is not so interesting if you are trying to do experiments where you have strong drives from the waveguide. So we tried to take the essence of this work that I talked about and then strip it to its core to make it even simpler. So we realized a system where we only have one qubit, acting as an artificial atom or as an emitter, coupled to a waveguide at 2 points. So instead of two qubits, there is one, but we have two coupling points. So this is a very simple system. If you think about the case where your couplings have some non-trivial phase, shown by these phi L and phi R, by picking these phases such properly, for example, you can take the left side arm to have 0 phase and the right arm to have pi over 2, you can get a situation where the emission to the waveguide, the components from these two coupling legs, constructively interferes when going in one direction and destructively interferes when going towards the other one, and that gives you a directional response. So I have to mention that these distances we are talking about are in general much shorter than the, if you normalize this distance by the speed of light, the delay you get is going to be much shorter than the radiative lifetime of these systems. So you are in the Markovian regime. You don't have to worry about temporal overlap of the emission from the qubits, so you can get very good interference. But then you can play these tricks where the phase allows you to have things propagate one way or the other. Now, thinking more about the details of how the Hamiltonian looks for this system, you can think about the continuum of electromagnetic modes into the waveguide and then write down your interaction terms at these points. So here is an example of a case where we are considering a strong drive with amplitude alpha propagating to the right direction. And then we have these components of coupling from the two arms, which gives us this 1 plus e to the I phase of the waveguide propagation minus the relative phase of the two arms showing up as a prefactor to the coupling. And this kappa em here is the decay rate of the emitter to the waveguide at one arm if you eliminate the other. So if your emission rate is kappa, your coupling rate to one of the modes is proportional to the square root of kappa. And then this is the phase factor. So if you redo the math and find the effective net emission rate to the right propagating mode, you get something like this, which has this 1 plus cosine term and can be set to 0 or to the maximum value of 2, this prefactor, by choice of these phases. And of course, you can repeat this analysis in reverse, and you will find that that phase term here has a negative sign that is different from the other case, which is just a redescription of the interference effect. Now, one note about the system. So far, I talked about chirality, which is talk about two transitions with preferences to propagate one way or another. This system that we are describing here, however, has to break Lorentz reciprocity. So the qubit has a single transition. If it propagates in one direction, it means that if you probe the system in the other direction, you see nothing, which means that the system has to break Lorentz reciprocity. And in terms of ways of realizing it, you can immediately think about using some sort of magnetic field in your experiment, which is a possibility, but superconducting qubits don't like magnetic fields, which is something we try to avoid. So another alternative way of doing it is to use some form of parametric drive to realize these phases required in this experiment and break the Lorentz reciprocity. And that's what we do in our experiment. So this is a module that is the simplest part that we can use to understand the experiment in. This E element is the emitter, which is the qubit acting as the quantum emitter I talked about so far. It's connected to the waveguide via two intermediate elements. One of them is a filter resonator. This is a cavity in the Purcell regime, so you can think of it as a radiation port to the waveguide. You'll see why we have it in a second. And this intermediate element here is a coupler element, which mediates interaction between these two other entities. So if you think about the coupling between this resonator and the qubit, we have a dispersive coupling, which would be a function of the capacitive coupling terms in each of these arms, some detuning related terms. And then interestingly, if you think about this coupler element, superconducting qubits can be frequency tuned via flux. So if you think about the case where we use a time periodic flux modulation to change the frequency of this coupler element, we can actually create multiple sidebands for this emitter radiating into the waveguide. So here you can see this is the phase, this is the flux threading this squid loop, having a constant term plus this periodic modulation, causing a frequency shift for the coupler element, which is also periodic with some magnitude and some phase. Now, if you think about the different sidebands of the emitter, the sideband that happens as at the original frequency plus the modulation frequency will have a coupling rate to this resonator, which is this big term. There is some Bessel function that is a function of the drive, and etc. But more importantly, it has this e to the I phi term, which is the phase of this pump used for flux modulation. So essentially, this is a nonlinear process. You don't need to understand how the details work, but the phase of the pump used in this experiment will be carried to the coupling rate that you effectively get between these two arms. Now, if you put two of these things next to each other, this is a waveguide, this is the emitter, these are the couplers, and these are the resonators. Yeah, you can get some net decay rate to the waveguide from each of these paths. As I said, these resonators are in the Purcell regime, so whatever coupling you have to them can be converted to some decay rate to the waveguide. The reason we have these resonators in place is that this parametric process creates multiple sidebands. We care about only one of them because the phases picked up by these different frequency components will be different. And we want to pick only one of them, so this resonator is actually acting as a filter, picking out only one of these and blocking the radiation of the rest of them into the waveguide. That's why we have it in here. And then we have the physical separation between the two ports, which is lambda over 4. This is how this system looks like. This center qubit is our emitter. These coupler elements are also, if you think about their hardware, they're actually qubits. These are all transmon qubits. So we have the emitter, we have this coupler element on the right and left. These on-chip ports apply these periodic fluxes. And then we have some planar resonator, which are the resonators described before. And they are coupled to a waveguide at two different points, separated by lambda over 4. In this case, lambda over 4 is about 4 millimeters. You can probe this system, and each of these components have their resonant feature that you can see by doing input-output microwave measurements. But the central feature here is the emitter response, which is what we are interested in. Now, thinking about the most basic response of a single emitter, we have this. If you think about, for example, the transmission through the system, if you probe it with some continuous wave drive, we have our familiar Lorentzian response in the transmission, which is a function of detuning the total decoherence rate in the system and the decay rate in the forward direction. Now, interestingly, if you compare the case of a chiral two-level system with a generic two-level system emitting in both right-hand and left-hand side, you can see that the magnitude of the transmission for a chiral system is actually flat. This is in absence of any intrinsic decoherence, so somewhat of a simplified picture. But interestingly, it doesn't have any resonant feature, whereas the regular bidirectional emitter has this resonant feature. By the way, these are theory curves. And if you look at the phase, in the phase you can actually see that the directional emitter has a phase response. The phase response qualitatively looks like a bidirectional emission, but the difference is that the phase difference across resonance is actually 2 pi for the directional case, whereas for the bidirectional or non-directional case, it's only equal to pi. So we can look for these signatures in our experiment. So these blue data points are results of an experiment where we probe this waveguide with a continuous microwave tone. So this is the transmission coefficient plotted in the complex plane. As you can see, the complex coefficient goes around the origin, hence the 2 pi phase that I talked about, which is a signature of a directional system. This dotted line is what you would expect from a bidirectional emitter, so these are quite different, showing you what you expect to get. And then you can look at the phase of this transmission, where you see this blue thing giving us the 2 pi phase that I talked about. We can also repeat this experiment in the opposite direction. This is, as you can guess, this is a setting where we have set these phases of the parametric drive such that we get maximal emission in one direction. But we can probe the system in reverse, and in reverse we see a flat phase because essentially we don't see any coupling to the two-level system. And these are, by the way, the amplitude of the transmission. This is the forward direction, and this is the backward. The forward direction is not completely flat, like I told you about, because we have some intrinsic decay and decoherence in the system, but it's still pretty large. And on the reverse side, we have something that is more or less flat, which is basically because we don't see the emitter. Now, one of the interesting features of this experiment is that we can control this relative phase this waveguide phase is fixed, but the relative phase between the two parametric drive tones can be changed in situ, which would allow us to change the radiation rate into the forward and backward direction in the experiment. So this blue curve is the gamma 1D forward, the decay rate in the forward direction, measured for different choices of this phase in our experiment. And in each setting, we can actually probe the system in reverse and find the radiation rate to the backward mode, which we can find is this red curve, and they're complementary. So we actually have full control over how much radiation we can get to the forward or the backward direction. Now, so far, this is basic functionality. We ideally want to benchmark this system to see how good or bad it is. One of the figures of merit that we can define for this system is the ratio of forward to backward emission, which tells us how directional this system is. This is an experiment in which we change the forward emission rate. We have nonlinear processes, so we can actually control these by choosing the power of the pumps in the system, so we can increase or reduce this. And we can see that for a range of forward direction emission rates, we can get directionalities that are well above 100. In fact, we think we are limited by how accurately we can measure the backward emission. As far as we know, the system has a very large directionality, which is at least 100. And then one of the things we had worried about in doing this experiment is the interferometric nature of the experiment. We have pumps, there is relative phases, they have to remain stable for this thing to work. So how useful it is, how can you expand this? These are all questions that we were asking. So one of the things we did was to directly measure the phase of our pump drives as a function of time. These are a few hundred megahertz classical microwave signals, so phase stability is really trivial. You just use a reference, and you can, if you look at the relative phase without even doing anything, the phase variation is really small. This is a 10-hour measurement. And if you look at this phase fluctuation and convert it to how much it hurts this directionality, you can find a bound by doing analytical calculation, which is about 1,000. So this is not really a big concern, which was a good thing. Another figure of merit is that we can define for this system is the rate of decay to the waveguide mode of interest in the forward direction divided to the intrinsic decay and decoherence. This is sometimes defined as waveguide cooperativity, or sometimes called as a waveguide Purcell factor. This number in our experiment can be increased. We can increase the forward emission rate, and then we can overcome the intrinsic decay. Within the limitations of our experiment, the largest number we can get is about 8, which is good, but not great. And in future, we can think about ways of improving it. I'd be happy to tell you more about it. So everything so far was weak drives and looking at directional response. Now, this system is in reality made from 2 resonators and 3 devices that are basically qubits, and there's the level structure of all these systems is very complicated. We have carefully designed it to have an effective 2-level system, but that needs to be checked. So these are experiments in which we increase the strength of the drive tone and look at the response of the system. This is the transmission coefficient being saturated, so essentially power saturation of the qubit, which looks like a 2-level system as we expect. This one is looking at the resonance fluorescence signal, the inelastic scattering of light by the 2-level system. If you're familiar with it, we can see these Malo triplets, which are signature of 2-level system is strongly driven. And if we look at this separation of the Malo triplet peaks with respect to the central peak and map it versus power, we get this perfect linear relation, which tells us that this system under a strong drive remains a 2-level system. And the strongest we could drive it without breaking this simple picture was the rate of drives normalized to the total line width to be about 10, which is sufficient to show that we have something acting as a 2-level system. Now, one final experiment that we did, which is noteworthy, is that so far I told about the 2-level system with directional radiation to a waveguide. In many experiments, you desire a more complicated transition. You usually want a transition that is forbidden. It doesn't radiate, to use as a memory. And you want an optically active transition to use as an interface. And you can use something like that, for example, to do qubit photon gates or create entanglement between qubits and photons. With superconducting qubits, as I said, the transmons have rather boring transition structures, but we can play tricks. One of the tricks we can play is we can think about the energy level of a transmon. It has this fundamental transition that I've been talking about so far, but it also has a higher frequency transition, which is at a slightly different frequency. We can try to make our system such that the G to E is forbidden, but the E to F is actually decaying to the waveguide. And that would be useful for this purpose I mentioned, for example, to realize the photon atom gate. And interestingly, we could do this in our system while while making the E to F directional. So I won't go to the details of this data, but we essentially can do two-tone spectroscopy to see the E to F transition. And now we can pick our parameters such that this time the E to F become directional, and the G to E is nominally protected from decay into the waveguide. And then we can go ahead and use time domain sequences to, for example, map the population from G to E and then probe the E to F and look at the phase response that we get from this transition emitting in the forward direction. And doing these experiments, we showed that this is possible even though our system was not designed for this. So I'm going to skip some of my slides because I'm running out of time. But looking ahead, we think we can, with simplifications, we can make arrays of qubits in which we can look into different interesting ideas. One of them is generating entanglement by driven dissipative schemes, and the other is propagation of pulses, as I mentioned. And to do that, we have to do a lot of engineering. We have ideas how to simplify this system, make the qubits more compact, and increase their Purcell factor. So with that, I conclude the talk. Thank you for listening to me.